Good morning, AP Chem. This is still Chapter 8, General Bonding Concepts. And we are going to do Section 9, Localized Electron Bonding Model, and Section 10, Lewis Structure, both which you had first year chemistry, so it's just kind of a quick review. And we'll do more examples of Lewis structure in class. So first, Localized Electron Bonding Model. A molecule is composed of atoms that are bound together by sharing pairs of electrons using the atomic orbitals of bound atoms. In normal speak, that means a molecular compound made from nonmetals share a pair of electrons between them when they bond. For example, a real quick example. A real simple example of the localized electron model of a molecular compound, two nonmetals sharing a pair of electrons between them to form a bond. They form a bond by sharing a pair of electrons, and this is the localized pair of electrons that is shared between them. And if you recall from first year chemistry, we usually write the Lewis structure for hydrochloric acid or hydrogen chloride like that. The localized electron is the original or single pair of electrons being shared between the two atoms in a molecule, our bonding pairs. The localized electron is that original line you draw in the Lewis structure between atoms. It is the pair of electrons that gets shared to form that bond, that original bond. So that's the localized. Think about the word localized. It makes sense. What we're going to basically do this chapter is you are going to be able to draw the Lewis structure of practically every molecular compound or polyatomic ion thrown at you. You're going to predict the geometry of it. That's the end of the chapter. That's the VSEPR, also something you did in first year chemistry. And you'll be able to describe the hybridization of the molecules based on section 1 of chapter 9. That's the only section we're going to do. Hybridization gets a lot more involved. We're going to keep it very simple. If you can count, you can do hybridization. Lewis structures. Lewis structure of a molecule shows how the valence electrons are arranged among the atoms in the molecule based on observations of thousands of molecules and helps to explain lab data. They get the noble gas electron configuration by sharing electrons. Please remember, ionic compounds achieve noble gas electron configuration. I call it NEGEC for short. By gaining or losing an electron, molecular compounds are going to achieve noble gas electron configuration by sharing electrons. All right, the steps for writing Lewis structures. Add up the total number of valence electrons for each atom in the molecule or ion. That's going to be the polyatomic ion. Total number of valence electrons for molecular compounds are the family number. Please remember hydrogen's on the left, but it is considered a nonmetal, 1. The skeleton. Attach the central atom to the terminals with a single line, a single bond, representing a pair of electrons. A central atom is either carbon, has the smallest subscript in the formula, is listed first in the formula, and it's never going to be hydrogen. Distribute the remaining electrons around the terminal atoms first. If any are left over, they go on the central atom. The octet rule, with the exception of hydrogen, will always be achieved for all the terminal atoms. Any exceptions to the octet rule revolve around the central atom, never the terminals. All your terminal atoms will achieve an octet with the exception of hydrogen, which likes a duet. Any exceptions to the octet rule, either going above 8 or below 8, will always revolve around the central atom. If you are short electrons, form double and triple bonds as needed. 2 electrons short, form a double bond. 4 electrons short, form 2 double bonds or a triple bond. These are going to be your delocalized, which we will tackle in the next video. So pencil and eraser, good idea. Only for number 4, only if you come up short are you forming double bonds. Remember, this is all theory. It can get really crazy if you start throwing down double bonds wherever you want. So we are going to follow a particular criteria. Only if you come up short, only if you do not make the octet rule on the central atom are you going to form double or triple bonds. When we get there, you're going to be doing the VSEPR theory, valence shell electron pair repulsion. You will also be able to tell me hybridization of the orbitals. That's going to be Chapter 9, Section 1. Hybridization, like I said, we're going to keep it real easy. Couple of comments about the octet rule. Your carbon, nitrogen, oxygen, and fluorine will always observe the octet rule. Most importantly, usually carbon will have 4 bonds. Usually nitrogen will be 3 bonds and a lone pair. Oxygen will usually have 2 bonds and 2 lone pairs. Fluorine will have 1 bond and 3 lone pairs. That's very typical for those 4 atoms. Second row elements, boron, and also include beryllium, because even though beryllium's technically a metal, every once in a while it's also in molecular compounds. Boron and beryllium can be happy with less than 8. 8's fine, never over 8, but they could also be 6 or less. Third row elements and heavier can exceed the octet rule by using those empty valence d orbitals. So your phosphorus, your sulfur, your chlorine, your bromine, your iodine, etc. They can have more than 8, and usually just up to 12. When writing Lewis structures, satisfy the octets first, then place electrons around elements having available d orbitals. In other words, the terminal atoms will always achieve an octet rule with the exception of hydrogen. Any exceptions to the octet rules, whether it be less than 8 or more than 8, is usually around the central atom. And I am going to do some quick examples on Lewis structures. Tally up the valence electrons first. Carbon has 4, it's in family 4. That's 4 valence electrons total for hydrogen, plus the 4 for carbon, 8 electrons. Your central atom's going to be carbon. So pick your central atom, attach the terminals to the central with a line that represents a pair of bonded electrons. This line is your localized electrons. Two, 4, 6, 8. I used all the electrons that I had, and it's bonded. Done. Octet rule applies for carbon. There's 8 electrons around it. Hydrogen's happy with 2, and there's 2 around it. Each line represents a pair of bonded, shared electrons, and these are the localized ones. So what would it look like if you were doing with just dots? On the right is the actual pictorial. Carbon has 4 valence electrons. Each hydrogen has 1. I represented the carbon valence electrons with the red dot and the hydrogen's valence electron with just the X. This is the theoretical Lewis structure. Notice that each hydrogen can pop right into that nice spot, and that localized pair of electrons being shared between the carbon and the hydrogen. Well, this would get pretty messy, so we decide to use a line to represent the shared pair. So the Lewis structure is the one on the left. This is the one we're typically used to. All right, this example is nitrogen trichloride. Again, these are all going to be molecular compounds. Molecular compounds are formed by sharing a pair of electrons between atoms. That pair of electrons is represented by a single line. That pair of electrons is the localized electrons. They are that first line you draw when you draw the Lewis structure. They do not move around. They're localized. Notice nitrogen is my central atom because it has the smallest subscript. It is written first. So it's my central atom. I attached the chlorines first with a single line to represent a pair of electrons. Then I distributed the remaining electrons to the terminals first. I had 2 left over that went on that central nitrogen. These two guys right here. I have 26 electrons in my structure. My chlorine and my nitrogens all achieved an octet rule. And if you notice, just like I said earlier, nitrogen has 3 bonds and a lone pair, which is very typical for nitrogen, just like it's typical for carbon to have 4 bonds. The cyanide ion has 10 electrons, 4 for carbon, 5 for nitrogen, and 1 extra one from the negative sign. All total valence electrons will be even numbers with the exception of 2 examples, which I'll do in the next video. There's only 2 of them that will not give you even numbers. So if you're getting odd numbers, and it's not those 2 examples, you are doing something wrong. 10 electrons. The carbon-nitrogen atom is forced to have a triple bond because there are not enough to go around. There are not enough terminal atoms. So your triple bond forms between the carbon and the nitrogen. I have 10 electrons in that Lewis structure. My carbon is satisfied with 8. My nitrogen is satisfied with 8. I have brackets around it to indicate an ion, which you always should, and the charge in the upper right hand corner to indicate it is an ion, because you have to indicate where did that electron, that extra electron, come from. Make sure you write your ions in brackets and the charge is indicated. Now notice nitrogen, yep, 3 bonds and a lone pair. Now carbon's a little different this time. Most times carbon will form 4 bonds. But here's an example where it's 3 bonds and 1 lone pair. What I really want you to know, and I want you to write down with emphasis, is this first line that I drew. This guy right here. This is the localized pair of electrons. This is that first line, that first shared pair that is the localized electrons. This line here and here, these are the delocalized electrons. These are the ones that can theoretically move around to form double or triple bonds. So it's kind of a definition-y thing. This is my last example, and then we'll do some in class. This is phosphorus pentachloride. It has 40 valence electrons, and again, take note, it's the valence electrons that are doing the bonding, not the core. Just like it's the valence electrons that get lost or gained when you're dealing with ionic compounds, it's the valence electrons that are being shared in molecular compounds. Phosphorus is obviously the central atom for the same reason as nitrogen was in the example above. It's written first, got the lowest subscript. So it's written first, and then I attached my terminal atoms with a single pair of electrons. Then I distributed the remaining electrons to the terminal atoms first. There were no extra ones, so there's no lone pairs on the central atom of phosphorus. Notice that phosphorus has 2, 4, 6, 8, 10 electrons around it because phosphorus is in that third energy level and can exceed an octet. So that's fine because he's got that empty d orbital to use, that 3d. All right, one more example. Same example I used a little while ago. All right, 8 electrons. Now this is a binary, so there's really no central. Any binaries, there's really no central atom. The line represents a pair of localized electrons. That's 2 electrons out of my original 8. That leaves 6 to be distributed. Well, they're not going to go around the hydrogen because hydrogen's already achieved what it wants, 2. Goes around the chloride. Your chloride, any of your halides really, will have 3 lone pairs and a bond. Here's what I want you to know also. Of the 2, the electronegativity of chlorine is greater than the electronegativity of the hydrogen, based on trend on the periodic table and numbers. Hydrogen's something like 2.20, chlorine's something like 3.16, 3.2. That's a difference of almost 1.0, so it's more electronegative. That means that this pair of electrons that's being shared between them is closer to the chlorine. That means that the chlorine bond has a slightly more negative charge on it at this end, and the bond has a slightly more positive charge at this end. You have a molecular bond that has a dipole moment. It is a polar bond. And it's indicated by the arrow pointing to the more electronegative atom in the bond. The other thing that I want you to remember, because you did this first year chemistry, is when we get into Vesper, and since it's a binary, it's going to be linear, you're also going to have a polar molecule. Since the bond is polar and it's a binary molecule in an electric field, this is going to align itself very deliberately in an electric field, and that means that the molecule is also polar. So a couple of things that's a refresher from last year. And I think that's it, folks.